Hi, welcome to the Olympiad geometry. Let's continue our study. Before we start, if you think this video is helpful, please click the like button, comment, share, and subscribe the channel. So today we're going to talk about the correlation of triangle centers. We already learned about the incenters, excenters, centroid, orthocenter, circumcenter. Right, that's the main five. The 9-point circle center. So that's main 6 triangle centers that we need to deal with in the Olympiad math. In the total, I think there are more than 60,000 centers already being discovered and discussed. But we are only focusing on 5 of them, and in the future, we will introduce several others of the centers that's very interesting and may occur in the Olympiad competition. So let's start. Property 1. In a triangle, the distance from orthocenter to any vertex is twice of the distance from circumcenter to the opposite edge. So I think we proved this many times before, but let's just do it again here. Because here we talk about the circumcenter and the orthocenter, so the audience should be already familiar with the procedure that we want to proceed, right? The first thing is that we find the vertex and connect the vertex to the circumcenter and extend it, meet the circumcircle on another point and find the relation. That's how we deal with this case. We repeated this several times already. I hope that's already be a pattern in your mind. So here would be A, B, C, and we call it H. So basically, let's consider about the orthocenter and the vertex A, right? So the distance from orthocenter to any vertex is twice of the distance from circumcenter to the opposite edge, right? The opposite edge of vertex A is BC, so it's basically ask us to prove that AH equals to twice of OM, right? So we just connect BO, extend it, meet the circle O on another point, let's call it D, right? Connect DC, connect AD. Okay, so because BD is a diameter, so angle BAD equals to 90 degrees, and angle BCD equals to 90 degrees, right? That means AD is perpendicular to BA, and we know that let's call it EFK. Okay, so we already know that AD is perpendicular to AB and CK is perpendicular to AB. That means AD is in parallel with CK. Similarly, angle BCD equals to 90 degrees. That means CD is perpendicular to BC and AE is perpendicular to BC. So CD is in parallel to AE, which means ADCH is a parallelogram. And that means AH equals to CD, right? AH equals to CD. And we know that O is a midpoint of BD. And the distance from O to BC actually is the distance from O to the midpoint of BC. So here is M. That means the distance from O to BC is OM, right? And we already know that O is a midpoint, M is a midpoint, so OM is in parallel and equals to half of CD, right? So we know that OM equals to half of AH. Okay, that's first property. And property 2. In a triangle, the circumcenter is orthocenter of the triangle formed by the projection points from circumcenter to 3 edges. Okay, so it's basically saying that we want to find a triangle that formed by the projection points from circumcenter to 3 edges. Actually, that's a midpoint, right? Midpoint of 3 edges, because we're trying to find the projection point from the circumcenter to each edge. Basically, we want to find the perpendicular bisector of each edge. So let me draw this here. I set it as MNP. And we want to prove that the circumcenter O is the orthocenter of the triangle formed by the projection points from circumcenter to the 3 edges, which means we want to prove that O is the orthocenter of triangle PMN. Okay, we want to prove that O is orthocenter of triangle PMN. Notice that P is a midpoint, M is a midpoint, N is a midpoint of AC, so PM is in parallel to AC, and PN is in parallel to BC. MN is in parallel to BA. That means OM is perpendicular to BC, and BC is in parallel to PN, means OM is perpendicular to PM. Similarly, OP is perpendicular to AB, and AB is in parallel to MN. So OP is perpendicular to MN. And ON is perpendicular to AC. AC is in parallel to PM. So ON is perpendicular to PM. That makes O to be the orthocenter of triangle PMN. Okay, that's property 2. Property 3. Property 3. In a triangle, the line defined by the incenter and any vertex is the angle bisector of the angle formed by the circumcenter, orthocenter, and the vertex. Okay, so let's draw a triangle here. I just want to save some space. Okay, A, B, C here. And we want to find the incenter. Let's call it D, E, F, I here. It seems that the line defined by the incenter and any vertex, so incenter, vertex, is the angle bisector of the angle formed by the circumcenter, orthocenter, and the vertex. So let's just choose A as a vertex we're talking about. So we want to prove that we find the circumcenter. Oh, I guess I have to draw a larger figure here. So That's enough. This is I, and let's just consider this as 90 degree. So this is H. Right, and the midpoint. I think the figure is not well drawn, but it's just a, okay. This is O. So we want to prove that A, this is I, this is O, this is H. We want to prove that AI is angle bisector of angle OAH. Right, that's our target. So the first thing is we know angle BAI equals to angle CAI. Right, we want to prove AI to be the angle bisector of angle OAH. Basically, we want to prove that angle OAI equals to angle IAH. And we already know that angle CAI equals to angle angle BAI equals to angle CAI. Right? So what about the angle CAH and angle BAO? So angle CAH equals to, see here, angle CAH. This angle equals to, this angle equals to 90 degree minus angle C, right? This angle, CAH, that's 90 degree minus angle C. And we already know that angle AOB equals to twice of angle C. So angle BAO plus angle ABO equals to 180 degree minus angle AOB equals to 180 degree minus twice of angle C, which means angle BAO equals to 90 degree minus angle C, right? Half of this. So angle BAO actually equals to angle CAH. So BAO equals to CAH and BAI equals to CAI. So we know that angle OAI equals to angle HAI. Right. AI is the angle bisector of angle OAH. That's property 3. Let's see property 4. In a triangle, the incenter and any vertex define a line which intersects the circumcenter on an intersection point. The line defined by the intersection point and the circumcenter is the perpendicular bisector of the edge that opposites to the vertex. Okay. So again, in this problem, we have the circle here. Let's just draw the circle first. I'm trying to find a way that we can see the problem. And so in a triangle, the incenter and any vertex define a line which intersect the circumcenter on intersection point, right? So let's just draw this one here. We have the circle, we have the triangle, and we want to find the incenter of the triangle, right? So basically it's saying that we want to connect the incenter and any vertex, define a line which intersects the circumcenter, actually this should be circumcircle, right, on an intersection point. So this is a circumcircle on intersection point. Let's call it D, right? So I is somewhere on this AD line. And we want to prove that the line defined by the intersection point and circumcenter is a perpendicular bisector of the edge that opposite to the vertex, which means if we connect the circumcenter to this intersection point, we want to prove that OD is perpendicular bisector of BC, right? But this is very obvious because AD is angle bisector of angle BAC. That means arc BD equals to arc DC, which means BD equals to DC, right? BD equals to DC. So D is a midpoint of arc BC, which means OD is perpendicular to BC, and also it's a perpendicular bisector of BC. Okay. So that is true. Let's see property 5. In a triangle, the midpoint of circumcenter and also center is a center of 9-point circle. Actually, we proved this before, right? In the chapter talking about the 9-point circle. So here, just to remind ourselves, let's review the 9-point circle, the concept of the 9-point circle. So we will cover the proof that the midpoint of the the midpoint of the circumcenter and also center is the center of the 9-point circle. So let's just consider. I don't think I need to draw the circumcircle, right? Right. The idea of the 9-point circle is that for a 9-point circle, okay, in triangle ABC, the foot of altitudes, that's DEF, right, and midpoint of each edge, which means here let's call it M, P. So, and also midpoint of the segment from a source center to each vertex, right? The midpoint here, here, and here. Let's call it X, Y, Z. Okay, so these 9 points are cyclic and form the circle called 9-point circle. So let's just consider that we have the circumcircle for the triangle FDE, right? And we want to prove that M is also on this circle. We can connect FD, connect DE, connect FE, and also connect FM, connect ME. Okay. So for angle ADE, so look at angle ADE, this one. Because HDCE, these 4 points are cyclic, so angle ADE equals to angle HDE, right? Also equals to angle HCE equals to 90 degree minus angle BAC. Right, this one equals to this one, and this one is 90 degree minus angle BAC. And angle FDA or ADF, this angle equals to, because FBDH are cyclic, so angle FDH or FDA equals to angle FBE, which equals to 90 degree minus angle BAC. So we know that angle FDE equals to twice of 90 degree minus angle BAC, right? So it equals to 180 degree minus twice of angle BAC. That's angle FDE. Now let's calculate about the angle FME. Right, so angle FME equals to 180 degree minus angle BMF minus angle CME. Right, and because M is the midpoint of BC, the triangle BFC is a right triangle. That means MF equals to MB equals to MC, right? So angle B, because MF equals to angle MF equals to BM, so angle FBM equals to angle BFM, right? Which means angle BMF equals to 180 degree minus twice of angle ABC, right? Similarly for angle CME, because angle BEC is 90 degree, M is a midpoint of BC, so ME equals to MC equals to BM. Because ME equals to MC, so angle the angle MEC equals to angle MCE, which means angle CME equals to 180 degree minus twice of angle ACB, right? So this one equals to twice of angle ABC plus angle ACB minus 180 degree, which equals to twice of angle ABC plus angle ACB plus angle BAC minus 180 degree minus twice of angle BAC, right? And this is 180 degree, so that's 360 minus 180 equals to 180 minus twice of angle BAC. Right, look at this one. It equals to this one. So we know that angle FME equals to angle FDE, which means FMDE are cyclic. Similarly, for point N and P, we can easily prove that they are all on this circle. Now we want to prove X or say FXDE are cyclic. So let's calculate the angle FXE. Angle FXE equals to angle FXH, right? Let's consider about the triangle BFH. That's a right triangle, and X is a midpoint of BH. So FX equals to BX equals to XH, and also angle FXH is twice of angle FBX, or say twice of angle ABE, right? Which equals to twice of 90 degree minus angle BAC. So it equals to 180 minus twice of angle BAC, which equals to angle FME or angle FDE. Right, that means X is also on this circle, and therefore we just prove that FPXMDENZ 9 points are on the same circle. That's called, and this circle called 9-point circle. Okay, that's great. And still we want to prove that the center of the 9-point circle is a midpoint of OH. So remember that we find the midpoint M here, midpoint N here, and midpoint of ABP here, right? So where is the circumcenter of the triangle ABC? We just need to find the perpendicular line of OM here and find the perpendicular line, this one here, right? It's called, let's call this as O. So the idea is that let me just move it on this side and enlarge it, right? So basically O is here, H is here, and we know that OM is perpendicular to BC, HD is perpendicular to BC, and also this is H, okay. Also, this point is P, this point is F, right? And we know that OP is perpendicular to AB, FH is perpendicular to AB, right? Basically, we want to find the center of the 9-point circle, and we already know that MD are all on this circle, which means the center of this circle must be on the perpendicular bisector of segment MD. So let's draw it here. That's a perpendicular bisector, right? And we know this line meet OH on a point. Let's call it V. So V, because this line is perpendicular bisector of segment MD, that means this line is perpendicular to MD and OM is perpendicular to MD. HD is perpendicular to MD. So this line is in parallel with OM, in parallel with HD, right? And because this equals to this, that means V is a midpoint of OH. And think about to find another one. I mean, let me just draw it like this. V prime. We find the perpendicular bisector of segment PF, and this line meet OH on another point. That's called V prime, right? The exact same procedure. We know that this point must be the midpoint of OH, which means V prime and V are the same point, and also they are on the OH, and they are, it's a midpoint of the OH, right? That's the center of the 9-point circle. Okay, so we just proved property 5. And for property 6, in a triangle, the circumcenter O or center H, centroid G, and the center of 9-point circle V are collinear, and OH to GH equals to this one, GV to VH equals to this one. Okay. So let me, I guess we draw another figure would be the easiest way. Is it? Yeah. So just remember that we proved one thing. Let me find. Okay. Here. So remember that we proved the circumcenter, the distance from circumcenter to edge BC, OM, equals to half of AH, right? And then we connect OH, connect AM, right? Because OM equals to half of AH, and also because OM is perpendicular to AD, right? Or AH, OM is perpendicular to BC, right? So we know that OM is in parallel with AH. OM is in parallel with OH, so it's easily to say, let's say AM meets OH on a point, call it P, right? So point P. So we know that OM is in parallel with AH, which means triangle OMP is similar to triangle AHP, right? These two triangles are similar. So OM to AH, that's 1 to 2, which means MP to AP is 1 to 2, which means P is a centroid, right? Because M is a midpoint, and we already know that for the centroid, AG to GM equals 2 to 1, and we know AP to PM equals 2 to 1. So this P is a centroid G. And then we know that OG to GH equals to 1 to 2. Okay, so think about the segment. We have O here, we have H here. The midpoint is the center of 9-point circle V, and we have G here, right? So OG to GH, that's 1 to 2. So OG is 1/3 of OH, right? And then look at the ratio we want to prove. we want to prove that OG to GH equals to 1, 2, 2, which we just did, and GV to VH equals to 1, 2, 3. So this is half, right? And this is 1/3 of OH, which means GV is 1/6 of OH, and VH is half of OH. So we know that GV to VH equals to 1, 2, 3. Okay. So for property 7, in a triangle, the incenter and excenters form an orthocenter group. The 9-point circle of the orthocenter group is a circumcircle of the triangle. The circumcircle equally bisects the segments from each excenter to incenter. So this is triangle ABC, IA, IB, this point, IC, right? Basically, it seems that in this triangle, the incenter and excenter form an orthocenter group. The incenter and the excenters form an orthocenter group. We just need to prove that I is the orthocenter of triangle IA, IB, IC. And we did that in the chapter talking about the excenter, and here we can still prove it. It's pretty straightforward, just because the angle ABC, let's call this point X, okay? The angle ABC plus angle CBX equals to 180 degrees. And ICIA is the angle bisector of angle CBX. BIB is the angle bisector of angle ABC. That means half of the angle BAC plus half of the angle CBX equals to 90 degrees, which means BIB is perpendicular to ICIA. Similarly, AIA is perpendicular to ICIB. CIC is perpendicular to IAIB, which means IA is also center of triangle IAIBIC. So the point I and points IAIBIC form an orthocenter group. The 9-point circle of the orthocenter group is the circumcircle of the triangle. Think about the 9-point circle. 9-point circle is a circumcircle of altitude's foot triangle, which means that is for the triangle IAIBIC, the foot of altitudes are ABC, right? The circumcircle of ABC is the circumcircle of the original triangle ABC, right? And it's saying that the circumcircle equally bisects the segment from each excenter to incenter, right? That's what we proved from the orthocenter. So in triangle IAIBIC, IA is the orthocenter, right? The midpoint of the orthocenter to the vertex is also on the 9-point circle, which here is the circumcircle of ABC. That means the circumcircle of ABC equally bisect the segment IA, which from the in-center to the x-center. Okay. That's property 7. Property 8. Let O be the circumcenter of triangle ABC. I be the in-center of triangle ABC. Then I is the orthocenter of triangle IAIBIC. We just proved that. The symmetrical point O prime, that from I to O, is the circumcenter of triangle IAIBIC. It's basically saying that we find the let me see if we can. This is roughly says a midpoint, something like this, right? And here is a midpoint, something like that. So this is still not a very good figure. Let me redraw it. Okay, so that's easier. Okay. Okay, so think about this problem. We want to prove that the symmetrical point from I to O is the circumcenter of triangle IAIBIC. So what is I? I is the orthocenter of triangle IAIBIC. What is O? O is the center of 9-point circle of triangle IAIBIC. Right? So we already know that the circumcenter for triangle, the circumcenter, the center of the 9-point circle, and the orthocenter are on the same line, right? Are collinear, and also the center of 9-point circle is a midpoint of circumcenter and orthocenter, which means this is orthocenter. This is a center of 9-point circle. So if we find the symmetrical point from I to O, that must be the circumcenter, right? So we just prove it. And we want to find the Euler line of triangle IAIBIC is IO. That's obvious because I is orthocenter, O is 9-point circle, center of 9-point circle. So that's a Euler line, right? Let's see property 9. Property 9. The area of a triangle is a geometric mean of the area of its x-centered triangle and the tangent triangle formed by the triangle and its encircled tangents. Okay. So it's asking us to calculate the relation between the area of a triangle, right? We want to prove that's the geometric mean of the area of its x-centered triangle. So we want to calculate for the area of the x-centered triangle and the tangent triangle formed by the tangent and the tangent triangle formed by the tangent and its encircled tangent, right? So formed by the triangle and its encircled tangents, which means we have a triangle here. We know the area, let's call it as triangle ABC, right? And we have the area of this. We have the area of this in-center tangent triangle. Let's call it DEF. And we know the area of triangle, the x-center triangle. So that's triangle IAIBIC, right? So we want to prove that square of this area equals to the production of area of triangle DF and the area of triangle IAIBIC. We want to prove this. Okay. So I'm not sure if you still remember that we proved a very important property before in the x-center chapter, but let's just review it. So for the triangle IAIBIC, right? For the triangle IAIBIC, here, for the triangle IAIBIC, we know the length of BC equals to A, AC equals to B, BA equals to C, right? Can we calculate for the relationship between BC and ICIB? BC and ICIB. So let's think about this. For triangle BIAC and triangle IBIAC, they both have the angle BIAC, right? And angle CBIA equals to angle CBIA, this one, CBIA equals to 90 degrees minus half of angle ABC, right? This angle is 90 degrees minus half of angle ABC. And we know that IA is perpendicular to ICIB. IC is perpendicular to IAIB. So AICIB, these 4 points are cyclic, which means this point, this angle, the angle IIBC equals to angle IAC equals to half of angle BAC. And this angle, the angle AIBI equals to angle ACI equals to half of angle ACB, which means angle AIBC equals to half of angle BAC plus half of angle ACB, which means it equals to 90 degrees minus half of angle ABC and equals to angle CBIA, which means triangle BCIA is similar to triangle IBICIA. Right, so BC to IBIC equals to BIA to IBIA. And the BIA to IBIA, that's sine angle BIBIA, right? And because angle BIBIA equals to angle IAC, which is half of angle BAC, so it equals to sine half angle A, right? BC is A, so which we got IBIC equals to A divided by sine half angle A, which is A times cosecant half angle A, right? We showed this before, but let's just review. We need it. So let's put it aside and think about another one. What about the length IIA? Because IBIAC, these 4 points are cyclic, and angle IBIA is 90 degrees. That means IIA is the diameter of this circle, right? The circumcircle of IBIAC. IA is the diameter. That means IIA times sine angle BIAC equals to A, right? And we know that angle BIAC equals to 90 degrees minus half of angle BAC. I think I just prove it somewhere, maybe not. Okay, it's very easy to show because angle BIC equals to 180 degrees minus half of angle B, half of angle C. That means the angle BIC is 90 degrees plus half of angle A. So, and this one plus this one is 180 degrees. That makes this one to be 90 degrees minus half of angle A, which is this one, right? So we got IIA times cosine half of angle A equals to A. Or we can write that IIA equals to A times second half of angle A. Okay? So, based on these two, let's consider IIA times IBIC, right? IBIC times IIA equals to IBIC times AIA minus AI, right? Which equals to twice of the triangle area IAIB IC minus twice of the triangle area IBICI, right? And also we can use this here. We can use it here. So IIA times IBIC equals to A times half of 1 over sine half angle A, right? That's for the IBIC part, and also times A 1 over cosine half of angle A, which is, we know that A can be written as 2R times sine angle A, right? So we can replace 1 of A here. So we got A times 2R sine angle A 2 sine half angle A cosine half angle A. So it equals to A times 4R, right? Because this can be replaced to twice of the sine half angle A cosine half angle A, right? So it equals to A times 2R. That's IIA times IBIC. Okay, so look at these two equations. We can write for the IIB times IAIC, right, directly. So that's B times 4. And also equals to twice of the area triangle IAIB IC minus twice of the area of triangle IAICI, right? And IIC times IAIB equals to C times 4R equals to twice of the triangle area IAIBIC minus twice of the triangle area IAIBI. So we sum them together, then we get 4, because 3 of them, that's 6 triangle area of a triangle IAIBIC area, right? And these 3 summed together, that's twice of the triangle IAIBIC area. So the total would be 4. 4 times the area of triangle IAIBIC equals to A plus B plus C times 4R, right? And A plus B plus C can be written as twice of the triangle area ABC 2R times 4R, right? So based on these two, we have the area of triangle IIBIC to the area of triangle ABC equals 2R, 2R. Okay, now we want to prove, so this is a thing that I want to show. Basically, we already proved this before in the X-center chapter, right? I just prove it again here because we need to use it. Now we want to prove that this one times triangle DEF equals 2 square of ABC. And we already know that this exists. Basically, the equivalent to prove ABC, the area of ABC to the area of DEF equals 2R, 2R. And now let's focus on this. Question is how to calculate the area of the triangle ABC with using the radius of the circumcircle R. Right, and we know that AB equals 2R sine angle C. Right, that's AB. And AC, that's 2R sine angle B. We can use half of AB times AC times sine angle A to represent for the area of triangle ABC, right? So it equals to half of 2R sine angle C, 2R sine angle B, sine angle A, which equals to equals to 2R squared sine A sine B sine C, right? That's the area of triangle ABC. So what about the area of triangle DEF? Right, we know the radius of the circumcircle of triangle DEF is R. So we want to calculate for the angle FDE, right? And we know that angle FDI, this angle, equals to this angle, which is half angle B. Similarly, this angle equals to this angle, that is half angle C. So angle FDE equals to half of angle B plus half of angle C, which is 90 degrees minus half of angle A. Right, similarly, we can get this one is 90 degrees minus half of angle C, this one is 90 degrees minus half of angle B. So we use a similar method to calculate the area. We know that the triangle DEF area equals to half of 2R times actually let's just write it as 4R squared times sine 90 degrees minus half of angle A sine 90 degrees minus half of angle B sine 90 degrees minus half of angle C, which equals to 2R squared times cosine half of angle A cosine half of angle B cosine half of angle C, right? And we know that we want to prove the area of triangle ABC to the area of triangle DEF equals to 2R by R. So let's just calculate here. It's actually R2R times R2R times sine A sine B sine C 2 cosine half A cosine half B cosine half C. Right, that's what we have here. And it's actually equals to R2R times 8 R2R times sine half angle A sine half angle B sine half angle C, right? So let's make it 4R to R2 is here, right? So basically we want to prove that this ratio equals to 2R to R. That means we want to prove this equals to 1, okay? Equivalent to prove that 4R to R sine half of A sine half of B sine half of C equals to 1. Okay, let's consider what is R2 sine half angle C. R is a distance from this one, from the in-center to BC, let's say, right? So R2 half of sine B, that equals to IB, right? Because this is half of angle B. So R2 sine half of angle B, that equals to IB, right? IB is here. And we know that this angle equals to this one, which is half of angle C. So let's continue use IB to sine half of angle IB2 sine half of angle C, that is IA. That is IIA. Right, and now we get 4R times sine, so equivalent to 4R times sine half angle A equals to IIA. Right, so I just did move the R to the right side of the equation and divided by sine half angle B sine half angle C, and then I got this one. So we want to prove this one here, and we already know IIA equals to A divided by cosine half angle A, right? That's IIA. So basically it equivalent to prove that 4R times sine half angle A equals to A times 1 over cosine half angle A, which is equivalent to prove that 2R equals to, or let's say this way, just move this cosine half angle here. So that's 2R times sine angle A equals to A. Right, and this is obvious. It's obviously true. So every step is reversible. So that means we just prove this one. Right. We just prove that the area of triangle ABC is a geometric mean of the area of x-center triangle and the area of the in-center tangent points triangle. Okay, that is property 9, right? And now let's look at property 10. Property 10 is a very interesting problem. So, property 10. The Euler line of the x-center triangle and the Euler line of encircled tangent triangle are the same line. Okay. Let me see if I can. Okay, let's just use this one here. We want to prove that the Euler line of the x-center triangle, right, and the Euler line of in-center in-center tangent point triangle are the same line. Right, we want to prove they are the same line. So look at IA here. Because IA is perpendicular to DEF, right? IA is perpendicular to FE. Why? Because AF, AE are the tangent line for the circle I. So triangle AFI and triangle AEI are congruent, which means FE is equally bisected by the AI, right? So AI is perpendicular bisector of segment FE. So AI is perpendicular to FE. And AI is perpendicular to ICIB. That means FE is in parallel to ICIB. Similarly, FD is in parallel to ICIA. DE is in parallel to IAIB. Right. That makes the triangle DEF and the triangle IAIB-IC to be similar, and also so we want to find the center of this similarity, which is difficult. But what we can do here is that we already know that point I, think about this. So in this such of similarity, if we have one line in, let's say, triangle IAIBIC, then we can always find the corresponding line in the triangle DF, right? And they will meet on the center of the whole figure. However, in this problem, the point I is a circumcenter of triangle FDE, which means I is on the Euler line of triangle FDE. And also, we already know that IO or IOO prime is the Euler line of the triangle ICIAIB, right? And because I is not necessarily be the center of the whole figure, that means these two Euler lines must be on the same line. Otherwise, this figure has two centers, which is impossible. Okay. And that's property 10. For property 11, let HGI to be the orthocenter centroid in center of a triangle with 3 unequal sides, then angle HIG is larger than 90 degrees. Actually, this one I believe we proved before. The basic idea is to find we can just draw a parallel line from the centroid to any side, right? And then we just need to prove that point I is inside the circle with diameter HG. Okay, that's very easy to prove. Let's just skip that for now and see the property 12 here. Property 12. In acute triangle ABC, the distance summation from circumcenter to 3 edges is set to DO. The distance summation from centroid to 3 edges is set to DG. The distance summation from orthocenter to 3 edges is set to DH. Then 1 times DH plus 2 times DO equals to 3 times DG. Okay, so let's so this is H, A, B, C, M. This is O, connect to OH, connect to AM. So this point is G. So we want to prove the summation, but because these 3 side has a similarity here, so we just need to prove one side, right? So we want to prove that O basically D, E. We want to prove that 1 times DH, which is HD, plus 2 times DO, which is OM, equals to 3 times DG, which is GE. We want to prove this. Okay, and remember that 2 times OM just equals to AH, right? It's a first property we learned from this video. So we translate it to 1 times HD plus AH equals to 3 times GE. Yeah. So 1 times HD plus AH, that is AD, right? We just need to prove AD equals to 3GE, which is very straightforward because the triangle MGE is similar to triangle MAD. So GE to AD equals to ME to MD, or equals to OG to OH, which is 1, 2, 3. Then we just prove it. That's property 12. And property 13. Oh, it's a long one. For property 13. In triangle ABC, the radius of circumcircle and incircle is set to R. The radius of X circle in angle A is RA, BC equals to A, CA equals to B, AB equals to C, then all of these. Okay, so just look at the things that we want to prove. It's all about a segment and square, right? And all of these segments actually are the distance from the centers, like OI, IG, HG, OG, OH, IH, IIA, IIB, OIA. That's all the distance from center to another center. Okay, so for this one, I believe you still remember that we need to use Stewart theorem. And now let's review the Stewart theorem. Stewart theorem is saying that in a triangle ABC, P is a point on BC. Then we have AP squared equals to AB squared times PC to BC plus AC squared times BP to BC minus BC squared times BP to BC times PC to BC. Okay, that's the Stewart theorem. So for this problem, let's do it in several groups, right? The first group is that we want to find the distance to I. We want to find the distance to I. Actually, any point, the distance from any point to I. And also we want to find the distance any point, okay? The distance from any point to G. And also we want to, so that includes, see, we have I, we have G, then we know the OG, right? Because that's any point. And for HG, we should know that's any point. For OH, we should know, because once we know the distance of HG, the OH, we directly know, we know the ratio, right? And for IH, we already know I, so this should be fine. For IIA, that's a little bit different, so let's just calculate the distance, any point, okay? The distance from any point to IA. Okay, let's do these three calculations. And then, once we finish all of these three, let's come back to this one here. So let's just put this aside. So the first one, we want to calculate for any point to the in-center I, right? The distance from any point to the in-center I. A, B, C, A, B, C. This is I. Let's consider this point. So this is D, this point is E, this point is F. And let's consider about the point P here. We want to calculate for PI squared. Okay? Connect AP, connect PC, connect EP, and connect BP. We know that PI squared equals to BP squared times IE to BE plus PE squared times BI to BE minus BE squared times IE to BE times BI to BE. Right, that's PI squared. What we have here, we know that IE to BE. That's AE to AB plus AE, right? Because AI is the angle bisector of angle BAE. So we know that IE to BE. We know BI to BE, but we don't know the length of PE, okay? And we don't know the length of BE, okay? So for PE, PE square equals to AP square times EC to AC, right? Look at the triangle APC and PE. So PE square equals to AP square times EC to AC plus PC square times AE to AC minus AC square times AE to AC times EC to AC, right? That's PE square. And we still have B square here. So BE square equals to AB square times EC to AC plus BC square times AE to AC minus AC square times AE to AC times EC to AC. Right, so from these three equations, we should get the distance square of any point to I. Right, let's calculate. So the first thing, BE square equals to AB square, that's C square times times EC to AC, which is A to A plus C, plus BC square, which is A square times AE to AC. Because B is an angle bisector of angle BAE, right? So AE to AC, that's C to A plus C minus AC square. AC square is B square times this thing. So A to A plus C times C to A plus C. Right. So look at these two. We can, this is C square A, this is A square C. So if we extract CA out, we left C here, we left A here. That means A plus C, and cancel with denominator A plus C. Then we have AC here, right? And we have AC here, so this can be rewritten as AC times 1 minus B square to A plus C square. Okay, that's BE square. And what about PE square? PE square equals to AP square times EC to AC. So that's AP square. We just write it down. AP square times EC to AC. That is A to A plus C plus PC square times AE to AC. That's C to A plus C minus AC square times, this is the same, so this should be a C to A plus C, right? That is PE square. And we cannot simplify this, just leave it there. Now we put the P square, B square back into here. Remember that we still need to calculate for IE to BE. IE to BE. Okay, let's calculate. IE to BE equals to AE to AB plus AE. Right. What's the length of AE? That is BC to A plus C. So this is BC to A plus C to AB is C plus AE, BC to A plus C, which equals to, we times A plus C on numerator and denominator. So here will be A plus C times C, and this is plus BC, and we can cancel the C out, right? So the rest of the part would be A plus B, this would be B, so here is B, so it equals to B to A plus B plus C. And similarly for BI to BE equals to AB to AB plus AE equals to C to C plus BC to A plus C, which is A plus C to A plus B plus C. Okay, now we get everything. Let's just calculate for PI squared. PI squared equals to BP squared times IE to BE, which is B to A plus B plus C, plus PE squared, which is this one. So AP squared times A to A plus C plus PC squared times C to A plus C minus AB squared C to A plus C squared. That's the PE squared times BI to BE. BI to BE, which is A plus C to A plus B plus C, right? And then minus BE squared, that's AC A plus C squared, A plus C squared minus B squared. Okay, I write this form times IE to BE, BI to BE. So B to A plus B plus C, A plus C to A plus B plus C. Right, let's simplify this one. A equals to PI squared equals to, so look at this one. It has A plus B plus C on the denominator. On the numerator, it's B times BP squared. For this one, we have A plus C cancel with this A plus C, so it's A times AP squared divided by A plus B plus C. For this one, we have A plus C cancel this A plus C, so for this one, we have C times PC squared divided by A plus B plus C, right? So for the first three terms, we can write it as A plus B plus C, and A times AP squared plus B times BP squared plus C times CP squared, right? That is the PI squared for the first three terms, and then minus A squared cancel one A squared, so we have A B squared C 2. I mean A plus C cancel another A plus C here, so we have A plus C, A plus B plus C. That's 1, and then minus. Look at this one. This one is actually A plus C plus B times A plus C minus B. So keep the A plus C minus B here and cancel one A plus B plus C here. And this A plus C cancel one A plus C here. So on the denominator, it's still A plus C, A plus B plus C, right? On the top would be ABC times A minus B plus C, right? So for these two, because this is minus sign, so it's, if we expand it, it's ABC. Let's just put this one back into here, right? Because this is minus sign, so it's plus B here. So B cancels. The rest of the part would be A plus C. Then A plus C cancel. So that is A plus B plus C. AP squared plus B, BP squared plus C, CP squared minus ABC to A plus B plus C. Right, that's a PI squared. Now let's calculate for PG squared. Right, this is a midpoint. So A, B, C, M, N, let's call it Q. So here this point is P, right? Similarly, we want to just connect to PN, connect to AP, BP, CP, right? And for the Stewart's theorem, we know that AP squared equals to AB squared times PC to BC plus AC squared times BP to BC minus BC squared times BP to BC, PC to BC. We know this is half, this is quarter. So it can simplify to be half of AB squared plus AC squared minus 1/4 of BC squared, right? So it would be easier for us to directly use this one into here. So we have, this one is G, right? We have PG squared equals 2 B, so PG squared equals to BP squared times GN2 BN plus PN squared times BG2 BN minus BN squared times GN2 BN times BG2 BN. Right, that's PG squared. And we don't know the PN squared here. We don't know the BG to BN. Actually, we know, right? BG to BN, that's 2 to 3. And we don't know the BN squared. So BN squared equals 2. Directly use this one. So that's half of AB squared plus BC squared minus 1/4 of AC squared. That's BN squared, right? And what about the PN squared? PN squared is similar. PN squared equals 2 half of AP squared plus PC squared minus 1/4 of AC squared, right? So we can directly write for the PG squared now. PG squared equals 2 BP squared times GN to BN, that's 1, 2, 3, plus PN squared, which is this one. So we have half of AP squared plus CP squared minus quarter of AC squared. That is PN squared, right? Times BG to BN. BG to BN, that is 2 to 3. And minus BN squared. BN squared is this one. So half of AB squared plus BC squared minus quarter AC squared. That's BN squared times GN to BN. GN to BN, that's 1, 2, 3. BG to BN, that is 2 to 3. So it equals 2. See here, these 2 and cancel these 2. So that's 1/3 of AP squared plus BP squared plus CP squared, right? And for here, it's minus 1/6 AC squared, right? And for this one, it's 2 by 9. And times this, that's 1 to 9. AB squared plus BC squared minus, actually plus, right? Plus 1 by 18 AC squared. This is 3 by 18. This is 1 by 18. So the total would be minus 2 by 18, which is minus 1 by 9, right? So it equals to 1/3 of AP squared plus BP squared plus CP squared minus 1 to 9 AB squared plus BC squared plus AC squared. Okay, that's the distance for PG. And now let's calculate for PIA. Oh, right, we want to calculate for PIA. Let's just think about point here, call it P. So we know we need to use the Stuart theorem. So we have to find use the PA, PB, PC as a variable, and we want to find PIA squared. So we need PD here, right? So what we need here, we actually need the relation between AIA and DIA. So because BIA is the angle bisector of angle CBX, right? Think about this angle equals to this angle. So if we calculate the area of triangle BDIA and the area of triangle ABIA, okay? BDIA and ABIA, that's actually the ratio of DIA to AIA, right? And it also equals 2 for triangle BDIA, that is half of BD times BIA times sine angle DBIA, to triangle ABIA, that's half of AB times BIA times sine angle ABIA. And we know that angle DBIA equals to angle XBIA, right? And XBIA plus angle ABIA, that's 180 degrees. So this sine result would be the same. And half cancel each other, BIA cancel each other, we have BD to AB. So it's equals to BD to AB. Okay, so DIA to AIA equals to BD to AB. And we know the size of the BD, right? Because the BC length is A, this is B, this is C. So BD, the length of the BD equals to, let me just write it here. BD equals to AC to C plus B, right? And then we know that DIA to AIA equals to BD to AD divided by C. So that's A to C plus B. Right, that's DIA to AIA, which means AD to AIA equals to 1 minus A to C plus B equals to minus A plus B plus C, right? Equals to this one. So now let's calculate for the PIA square. First the PD square. PD square equals to PIA square times AD to AIA plus PA square times DIA to AIA minus AIA square times AD to AIA times DIA to AIA. Right, what's the length of the PD? PD square equals to BP square times CD to BC plus PC square times BD to BC minus BC square times BD to BC times CD to BC. Right, that's PD square. So we have the PD square now. And what about the PI? We're looking for PIA square, right? And for the AD to AIA, we already know, right? AD to AIA, we already know. So PA square, that's fine. DIA to AIA, and we already know. AIA. Because we already know the length of the AD, right? The length of AD square equals to AD square equals to C square times C square times DC to BC, which is B to B plus C plus, that's AD square, right? This one, and the AC square, which is B square times C to B plus C minus A square times B to B plus C times C to B plus C. Right, so we know the AD square, which is BC 1 minus A square 2 B plus C square. Right, that's the AD square. And we know the ratio of AD to AIA. Right, AD to AIA is this one. So we know the AIA. AIA square equals to AD square times AIA to AD square, right? Which is BC 1 minus A square 2 B plus C square times AIA to AD, which is B plus C 2 minus A plus B plus C square. Right, so it equals to BC times B plus C square minus A square 2 minus A plus B plus C square. Right, this one can be further written as so we have B plus C minus A and B plus C plus A that equals to BC times A plus B plus C 2 minus A plus B plus C. Okay, so we have all of them. Now let's calculate for the PIA square. Okay, I need another paper. Let's just do the calculation. So for here, the PD square equals to BP square. Let's just write it down. BP square times CD to BC. CD to BC, right? CD to BC, that is B to B plus C. Okay, this term is finished. plus PC squared times BD to BC, BD to BC, that is C2B plus C. So this term is finished, minus BC squared. BC squared is A squared times BD to BC times CD to BC, which is B to B plus C times C to B plus C, right? All of these is a PD square, which is here. It equals to PIA square. That's the thing we're looking for, times AD to AIA. AD to AIA is minus A plus B plus C to B plus C. So we finish this term and plus. Right, we finish this term plus PA square or AP square times DIA to AIA, which is here. The DIA to AIA, that is BD to AB, right? So DIA to AIA is A to B plus C, okay? We finish this part, minus AIA square. So AIA square is this one, BC, A plus B plus C, 2 minus A plus B plus C. That's AIA square times AD to AIA, which is this one, minus A plus B plus C, 2 B plus C, times DIA to AIA, which is this one, A to B plus C. Okay, that's what we have here. Now let's simplify it. The first thing is that I want to move this one on the left side. Actually, I want to move all of these on the left side, just to keep this on the right side, right? So we have minus AP squared to B plus C plus BBP squared to B plus C CP squared to B plus C, right? And minus B plus C square A squared BC. So we move this one. Now let's move this one. That's plus, right? Plus. And these two cancel each other. So we have ABC, A plus B plus C, 2 B plus C minus A plus B plus C. And it equals to PIA squared times minus A plus B plus C to B plus C, right? So now we move this term to the left side. We multiply B plus C divided by minus A plus B plus C. So for the first term, we have minus A plus B plus C to B plus C times B plus C 2 minus A plus B plus C, right? AP squared plus BP squared plus CP. Oh, sorry, no, this cannot be. No, this is wrong, right? Just cancel this one. So we have minus A plus B plus C. That's the denominator, and on the numerator, that's A minus A, AP squared plus B, BP squared plus C, CP squared, right? Sorry, this is correct now. And for here, minus I think I did something wrong here, right? Because these two cancel each other. So we have ABC times A plus B plus C, that's for sure. But for here, it's not this one. Should be square, right? Okay, that's correct now. B squared, B squared. So this one, square, square, and we have a minus A here. We basically cancel this minus A out, right? And we left B plus C, cancel that's B plus C. So it's actually ABC to B plus C and plus sign. So we have plus sign here times B plus C divided by minus A plus B plus C. So it's ABC2 minus A plus B plus C. That is PIA squared. Okay, now let's look at the problem we have. So we want to calculate for OI squared. We know that PI squared is this one. OI squared is just replace P to O, which is AO squared, BO squared, CO squared. That's R squared. So R squared extract out ABC cancel each other, which means IO squared equals to R squared minus ABC to A plus B plus C, which is R squared minus 2RR, right? So this is, I mean, we proved this many times, so I just simplify it here. And for IG squared, right, we can use okay, so we can use either way, right? Think about this one. We can just find AG squared, BG squared, and CG squared, right? What is AG squared? AG squared is 4/9 AD squared, right? Let me find a figure here. So let's see this one. What is AG squared? AG squared is 4/9 AM squared, right? And we can calculate for AM squared, which is half of AB squared plus AC squared minus quarter of BC squared, right? So it equals 2/9 C squared plus B squared minus 1/9 A squared. That is AG squared. So similarly for BG squared should be 2/9 A squared plus C squared minus 1/9 B squared. And CG squared should be 2/9 A squared plus B squared minus 129 C squared, right? And we'll have all of these. Let's just put it back into AG squared plus BG squared plus CG squared 2A plus B plus C minus ABC 2A plus B plus C, that is IG squared, right? And we want to calculate for something like this. So yeah, I'll just stop here because this is basically very simple calculation, right? It's very straightforward now. I mean, we already find the general equation. The rest of the part is just a hard calculation. Bruce follow calculation. So for OG squared, right? For OG squared, let's find the PG squared here. For this one, think about OG squared, that make AP to be R squared, BP to be actually, yeah. So that's AO squared, BO squared, CO squared, right? So that's R squared, 3R squared cancel with this 1/3, so it's r squared minus r squared here minus 129 a squared plus b squared plus c squared, right? So basically, look at this one and this one here, right? That's the same. For hg squared, that's a later difference. The difference is that we want to calculate for AH, right? And remember that AH, let me use this figure. Remember that AH equals to DC, which is BD squared minus BC squared, right? What is BD squared? That's 4R squared minus A squared. So AH squared equals to 4R squared minus A squared. Now let's put it back to HG here, right? For here. That means AH squared is 4R squared minus A squared. Then we have right. Then we have 1/3 of 4R squared minus A squared plus 4R squared minus B squared plus 4R squared minus C squared minus 129 A squared plus B squared plus C squared. Right, this one. So look at these two. Right. Let me okay. These two. Right. So it equals to 4R squared minus 429 A squared plus B squared plus C squared, which is same to this one. Right. And for OH, consider about HG to OH. What is HG to OH? That is 2 to 3, right? That means OH squared equals to 9/4 times HG squared. We already know the HG squared as this one. Divided by 4 times 9. We got 9R squared minus A squared plus B squared plus C squared here. Right. Okay. For IH, the first half is similar that we use distance to I, right? So this 4 comes from 4 squared minus A squared, something like that, right? It's very straightforward. But for the second part, I have to say I didn't find a way easily to prove this one in the constraint on the pure plane geometry method. I have a method that we can use polar coordinator and set the triangle ABC to be alpha, beta, gamma, and then use this one to false brutal to prove it. But it's kind of like we need the complex number. So I don't have a good idea how to prove it in the pure plane geometry way. So if any audience know how to prove that, please contact me, and we can discuss, and I can show this to others. Thank you. So for the rest part that we want to calculate for IA square, basically we want to calculate for the AI, the distance of AI, BI, CI, right? And then we replace it in the only thing here a little bit tricky is what is 4r times RA. Basically, we already know that 2RR equals to ABC by A plus B plus C, right? And you can easily prove that 2RRA equals to ABC2 minus A plus B plus C. Use the same method to just use the area of the triangle ABC, and you can prove this, and just replace it in. Okay. For the OIA square, that's very easy. Okay. Okay, so for this thing, we just finish it here, and we have some other properties here. Let's continue. Property 14. Property 14. Let R star be the radius of the circumcircle of triangle IIBSC. O star be the circumcenter of triangle IIBSC. Then the first thing that R star equals to 2R. Actually, we already proved this. Just use the 9-point circle. This is very straightforward. We actually prove this twice. Okay. And property 15. All of these properties are very, very straightforward. It's basically you just read it, you understand it right away. I don't think there's anything that we really need to elaborate here. Let's just move on to property 16. Property 16, let P be a point in the plane of triangle ABC. Line APBPCP meets the circumcircle of triangle ABC on A prime, B prime, C prime. Then, if P is a circumcenter of triangle ABC, so what we are doing here, let me find the paper. Okay, it's here. Basically, we want to, let's just consider that P is a circumcenter, okay? So we draw the circumcircle here. This is a circumcenter O, connect to AO. Meet BC on arc BC on A prime. This one is on B prime, and this one is on C prime, right? So we want to prove that for acute triangle, the area of triangle ABC equals to the area of triangle A prime BC plus area of triangle A B prime C plus area of triangle ABC prime. Okay, so ABC, the area of ABC equals to this triangle plus this triangle plus this triangle. Let's just connect it. Okay, so think about this one. The O is a center. The O is a center, and OC prime is a radius. OB, OA prime, OC, OB prime, OA, all of them are the radius. And we know this angle equals to this angle. So this one equals to this one equals to this one equals to this one, which means C prime B is in parallel with B prime C. Similarly, AC prime is in parallel with A prime C. BA prime is in parallel with AB prime. Okay, so based on that, we know BOB prime is a diameter in triangle BC prime B. In triangle BC prime B. Or let's see, let's just change another one. It's fine. In triangle B, okay, in triangle B, C prime, B prime, right? O is a midpoint. That means the area of triangle BOC prime equals to the area of triangle OC prime B prime. Right. So, what I'm trying to say is that, sorry, the area of triangle BCO actually equals to the area of triangle C prime BO. Right. So this one equals to this one. Right. And this one equals to this one. Right, but we just consider about this and this. For this one, it equals to this one. Right, that means the area of triangle ABC equals to the area of quadrilateral C prime B, B prime A. And C prime B, B prime A is identical to B prime C, A prime B. That means the area of triangle ABC is half of the area of AC prime B, A prime C, B prime, which means the rest part of the three triangle area summation would be same to the area of triangle ABC. Okay. So if P is also center, if it's non-acute triangle, then this would be minus. This would be very easy to prove. Use the same method, just find the equal area. Okay, so if P is orthocenter, conclusion is same to 1. Okay, if it's orthocenter, let's just draw the figure first. This is an easy one because we proved it before. The most important part we already done. Okay, like this. We know that HD equals to DA prime. That makes the area of triangle BHC equals to the area of triangle BA prime C. The area of triangle AHC equals to the area of triangle AB prime C. The area of triangle AHB equals to the area of triangle AC prime B. So, the summation of these three triangle area would be the summation of these three triangle area. Right, that's straightforward. For the acute case, we just need to prove it still keeps the this distance equals to this distance. Okay, for the case of centroid, we want to prove that the area of triangle ABC is smaller than these three triangle area summation, right? It's actually an interesting one because for the centroid, if you look at the connection, it looks like this. So think about the think about what we learned already. We know that if this point is on the circumcenter, we know the rest part, the summation of the rest part of three triangle area would seem to the triangle ABC, the area of triangle ABC, right? Then we just consider about the case that we are choosing this P point as a centroid, which means we basically connect the midpoint of BC down to here. And it's obvious that the height, the altitude of this new triangle would be higher, would be larger than the altitude of the triangle that passing through the circumcenter, which means the area of the triangle that passing through the centroid is always larger than the area of the triangle that passing through the circumcenter. The only exceptional case would be the equilateral triangle, right? Because in that case, these two lines are the same line. Okay. If P is the in-center, conclusion is the same to 3. Yeah, P is the in-center is like the best case, right? Because when P is in-center, we know that this connection actually meets the midpoint of arc BC, which has the largest altitude for this triangle, right? So that's certainly the largest one. Okay, property 16, we just finished. Property 17. In triangle ABC, the distance from in-center to circumcenter equals to the distance from centroid to circumcenter if and only if a squared plus b squared plus c squared equals to 18RR. So the distance from in-center to circumcenter, which is IO, right? And the distance from the centroid to the circumcenter, which is GO or OG, right? So let's just read it before. OI, which is R squared minus 2RR equals to OG, which is R squared minus 129 A squared plus B squared plus C squared, which means 18RR equals to A squared plus B squared plus C squared, right? So we just prove it. Okay, that's property 18. If and only if at least one angle in triangle ABC is 60 degrees, the distance from in-center to circumcenter equals to the distance from in-center to orthocenter, right? That is IO. In-center to orthocenter, that is IH. Okay. So we want R squared minus 2RR equals to 4R squared minus A to the power 3, B to the power 3, C to the power 3 plus A, B, C to A plus B plus C. Right? We want OI equals to IH. So this should be valid. And remember this one, we can rewritten it as 2 minus 2RR. That's actually ABC to A plus B plus C. So these two cancel each other. Then we basically want to prove that 3R squared equals to this one, right? And what is r squared? What is r squared? R squared can be, remember that the area of triangle ABC equals to ABC divided by 4r. So r squared can be written as a squared b squared c squared to 16, the area of triangle ABC, which equals to a squared b squared c squared to 16. Oh, here's square, right? 16 p minus a, p minus b, p minus c times p, right? Which is, this is a half, minus a plus b plus c divided by 2. So we just split this 16 to 4 2s, right? Then we got a squared b squared c squared 2, a plus b plus c minus a plus b plus c, a minus b plus c, a plus b minus c, right? We want this one times 3, right? That's 3r squared equals to this one. Okay, we want to get this one. So here I don't want to do the lengthy calculation because simplification of this one is really lengthy. I'll just put the result here. I got a squared minus ab plus b squared. I believe it's minus. Yeah, minus c squared. And then we have a squared minus ac plus c squared minus b squared, right? And then b squared minus bc plus c squared minus a squared equals to 0. Right? If we simplify this, we get this one. And once we get this one, we know that either one to be 0, right? Let's just choose this one to be 0. And we already know that b squared minus c squared can be written by the cosine law. So that is a squared plus b squared minus 2ab cosine c, right? Equals to 0. So we got 2 cosine c equals to 1, which means cosine c equals to half, which means angle c equals to 60 degrees. Okay, that's the way we do. It's just this one from this one to here is really complicated. Please do it by yourself as a practice. That's property 18. And for property 19, in triangle ABC, the incenter, circumcenter, orthocenter, and 2 vertices are cyclic if and only if the angle of the other vertex is 60 degrees. Okay, let's consider about the case here. So we have a triangle, right? Actually, let's just draw the circle. We have the triangle that the incenter and circumcenter and the 2 vertices are cyclic, right? I know orthocenter is also cyclic, but let's just consider about the circumcenter and the incenter first, right? So we have the triangle like this, A, B, C. the circumcenter is here, and the incenter is somewhere, right? And we know that BOC, angle BO, because BC and the circumcenter and the incenter are cyclic, so angle BOC equals to angle BIC. Right, angle BOC equals to angle BIC. And angle BOC, that is twice of angle A. Angle BIC, that is 90 degree plus half of angle A, which means angle A equals to 60 degree. Okay, and for the case that, now let's just prove that orthocenter is also on, right? So for the orthocenter, let's do this way. We want to calculate for the angle BHC, right? The angle BHC, equals to angle BHD plus angle DHC. Right? The angle BHD equals to this one, equals to, so let me just draw it. This one equals to this one. And we know that this one plus this one equals to 90 degrees. This angle plus this angle equals to 90 degrees. So angle BHD equals to angle ACB. Right, angle BHD actually equals to angle ACB. And similarly for this one and this triangle here, right, this one plus this is 90 degree, and this one plus this one is 90 degree. So this one is angle ABC. Right. That is since the angle BHC equals to 180 degree minus angle BAC, which equals to angle BOC, that is twice of angle BAC. So we know that angle BAC equals to 60 degree. Okay, that's property 19 and property 20. Property 20 is simple. It's just the same that P is a point on the triangle ABC. Line AP, BP, CP, AB, CP meet BC, AC, AB on DEF respectively. Then PD to AD plus PE to BE plus PF to CF equals to 1. Right? We can just use the area, right? PD to AD, that's area of triangle BPC to area of triangle ABC. PE to BE, that's the area of triangle APC to area of triangle ABC. PF to FC, that's the area of triangle APB to area of triangle ABC, and the summation would be 1. Okay, so we take about I don't know, maybe close to 2.5 hours to talk about the correlation of the triangle centers. Of course, this is just a part of it. there are too many properties, but these are the very frequently used one. So I hope you like this video. I hope you enjoy the derivation we did and be familiar with this concept, and we can use all of them in the very difficult problems. Hope you like it. See you in next one. Thank you.